Okay, so in our second stoichiometry podcast, you can feel free to try to say stoichiometry 5 times fast. I can't even say 5 times fast, so you're already better off than me. We're going to look at mole-to-mole stoichiometry, and these are basically one-step problems, very similar to the one-step mole problems that we've done so far, except now the conversion factor, like we said in the previous podcast, is your mole ratio, the ratio of the moles of the substance you want over the moles of the substance you're given. So, here's what we need to do, and I just need to tweak something here for just a minute so it looks right. There we go. And let's get right to it. So, this equation is something that you're probably experiencing right around this time of year. It's spring. The weather's getting warm. You're more inclined to go outside and grill out on the patio, have some friends over, drink some sodas, have a good time. So, this equation that we're looking at represents the burning of propane in a gas grill. So, anytime you buy that big tank of propane and burn it to produce fuel, to produce heat, to grill things, that's what you're doing. And I've already balanced it for you just to save us some time. So, step one is always, in this case, to get a balanced equation. So, we're going to check that off because we've already done that. Now, anytime you're starting a mole-mole stoichiometry problem, and you're given a number of moles, like we are here, we need to write the number of moles of the given substance in the upper left-hand corner. So, let's look at part A of this problem. It says, how many moles of oxygen are required to burn 3.0 moles of propane? Now, propane is C3H8. It's the one thing you wouldn't know there, so you could probably figure that out if you needed to. So, we're going to write that, just as we said, up in the upper left-hand corner. Now, it's really, really important, like I said in the previous podcast, to make sure you put in that formula. A lot of you have been getting, frankly, a little sloppy with your units, with keeping track of things, and it's caused you to make some silly mistakes. Now here, you're going to do that even more often if you don't not only write the unit, but the substance that it comes from. In this case, we need to be really specific that we have 3 moles of propane, C3H8. It's not 3 moles of anything else, it's 3 moles of propane. So, the next step is to use the mole ratio as a conversion factor. Now, in this case, it gets a little tricky because up to this point, we've either been canceling out moles or we've been canceling out something else, like grams or liters or something like that. In this case, we are going to cancel out moles. But we are not just going to cancel out any old moles. We're going to cancel out the moles of the substance we're given. And to do that, just like in any other problem we've done, we need to put that on the bottom. Now remember, from the previous podcast, that the mole ratio is derived from the balanced equation. So, we see in this balanced equation that we have no coefficient in front of C3H8, in front of propane. So, what we're going to put down here is 1 mole of C3H8. Now, that's nothing new. That's something that we've done a lot of times. But in this case, we're putting 1 mole of C3H8 on the bottom because there's only 1 mole in the balanced chemical equation. Now, if we want to convert to oxygen, in this case, O2, we need to use the coefficient in the balanced chemical equation that deals with oxygen. And in this case, we see that coefficient is 5. We have 5 moles of oxygen for every 1 mole of propane. So, we put our 5 moles of O2 on top. We cancel out the units that we can. And in this case, we can cancel out the moles of propane. We're left with the moles of oxygen, which is exactly what the question asked us. And so 3 times 5 is our answer. And I would like to think that we can all do that in our head and figure out that we would need 15 moles of oxygen to be able to burn that 3 moles of propane that we started with. So it really is that easy. Now, the tricky part for most of you is going to be remembering to use that mole ratio in your problem. So be really, really careful to make sure that in this one step, in the mole ratio, you use those coefficients from your balanced chemical equation. So I'm going to move right on down to part B. How many moles of water vapor, and that's just H2O, would be produced when 3 moles of propane are burnt. So we start with the same 3.0 moles of propane, and we have to use that 3.0 before anybody gets annoyed because we're dealing with sig figs here. We're dealing with precision. So, on the bottom, we're going to put the same 1 mole of C3H8 that we had previously because there's still a coefficient of 1 in the equation. And then, if we're being asked about water vapor, we need to find the coefficient for H2O to put in our other step, because that's the moles of the substance that we want, or our desired substance. So, we have 4 moles of water over the 1 mole of propane, and basically the math, once we cancel out our units, is 3 times 4. And 3 times 4, which again, I hope you know, is 12. So we end up with 12 moles of water. Hopefully that makes a little sense. We'll be getting some practice on that later on, so the more you see this stuff, the better off you're going to be. I think those of you who went from knowing nothing on the last test to getting really good grades, A's and B's, you can attest to that. So, if this isn't clicking right now, we're going to get some practice in class to really help you out. So, hope you like it.